Guillermo. How you doing, Guillermo?
Hello, hello.
Hi, you hear me okay?
I hear you well. What's today? What are we gonna do today? Some crazy physics to the secrets of the universe, maybe?
Yeah,
Just
we're really getting to that. Yeah,
just some boring structure of I'm kidding. It's not boring. It's fascinating.
Well, we'll get to the standard model today. At least start it. Yeah, a little more. I want to run through the Baryon Octet and the. Say, have you? Oh, I'm glad this is working. I was having such a time trying to get my new computer to work right.
Would you get the new iMac series or what?
Yeah, I did, and it's really nice, but for some reason the Zoom's not working. Hi, Kevin. How you doing this morning?
I'm alive. I'm doing good.
Yeah, I'm not sure what the problem is. I've got to sort out Zoom. Somehow it's not recognizing. So now we're going to be at a little different angle today because I'm back to my old computer. I don't know what the problem is, but I think you'll be able to see the board okay. So Guillermo, what you were finding octets and young tableau less than your greatest hopes for understanding the universe, or?
It's okay. I mean, it's an honest response. It's fine.
Yeah,
It's
no,
nothing.
I want to get your take on that. Yeah, it's a bit historical, right? This is
and I can understand that. Like, it's the process of it.
Yeah, the eightfold way is, it's just this approximate symmetry, right? But it's the right octet, and it's the right decaplet, the right octet. You're seeing all the right particles organized the right way, but within the standard model, it arises from SU3 color, not SU3 flavor. So let's see, is the difference there clear? I haven't really talked about color yet. I'll get to that.
Flavor and color?
Yeah. Yeah, that's what they're called, right? That's, people needed names for the properties. These are new properties. One doesn't really know how else to characterize them and to just make up some names.
Yeah, that's fair.
But what's all right? For example, what motivates color was it really gets down to the exclusion principle. Fermionic wave functions need to be totally antisymmetric, and in order to accomplish that, you have to weigh in, whatever symmetries you have, the spin wave function, the quark wave function. So you've got a spatial distribution, it's coupled to spin, and then any additional symmetry. And let's see, what was it? Looking at the, I think it's the decaplet. The omega minus is a down, down, down combination of quarks. And that has to be, you can't anti-symmetrize that. That's got to be a symmetric combination of the down quarks. If that's symmetric and you have an S state, you have a ground state. I mean, they see the particle, right? So it exists, except that, it's got to have a symmetric spatial wave function to be in the S state, the ground state, and it's got to have symmetric wave function to have the 3 identical quarks. And it was suggested by, oh gosh, I forget the Russian's name. I've written some, you know, a brief history of the development of all this, and I don't think I've posted that version of the text yet, but I'll get it up before we head off. It needs to be anti-symmetric, and that suggested first to this Russian grad student of, I think it was one of Bolgoyevov's graduate students who observed this in a footnote that, you know, it looked like there needed to be another quantum number in order to make this wave function anti-symmetric. And then, let's see, oh, was it Gilman, Glasgow? You know, some other people were making the same observation about the same time, shortly thereafter. And yeah, it was Gilman, I think Glasgow as well, who came up with the idea that it was an SU3, and Gilman actually predicted the 8 gluons at that point. Let's see, I'm not sure why they decided it had to be an SU3, but that was the origin of the SU3 color, and they just called it color because, you know, what are you going to call it? It's this property. You don't know what it is. I mean, it's sort of like isospin or something, right? It's you know, it's a little like spin, so we'll call it isospin. It's like spin, but different. It's the same group, but that doesn't mean anything. You know, lots of things have that group. So that's when they started using SU3 color. And, you know, people would just pick 3 colors, red, green, blue, or red, yellow, blue, or different people had different favorite colors. Gilman named them quarks after Finnegan's Wake, right? 3 quarks for Mr. Mark. And it leads to the same octet that you see with the Young tableau and the approximate SU3 symmetry that people had been using. Only now it's an exact symmetry. And it took about a decade for that to be to demonstrate the properties that had to be satisfied. There were things like asymptotic freedom. You had to show, let's see, there are a few properties, but, you know, anyway, it took about a decade and a few Nobel Prizes, in fact, before SU3 color was actually generally acknowledged to be a valid symmetry to be using. So that's what's built into the standard model. So we're, you know, I do want to talk about the baryons a little bit, but the standard model really starts with SU3 color. And so it's called quantum chromodynamics as the underlying symmetry of the strong interaction. And that predicts an 8-dimensional Lie algebra. Each generator of the Lie algebra leads to a gauge field. And those gauge fields represent the 8 gluons. Those 8 gluons can interact with any quark. Each quark is then thought to come with this additional property, right? And again, this is some property we can identify the quarks as having. It's named color for lack of any other information about it other than its SU3. So the conserved quantity is color. Color is exchanged by the gluons between the quarks. Each quark, you know, like an up quark can come in red or yellow or blue. You know, any one of these 3 different quantum quantum numbers. And let's see, when you do that, and I'm going to write this all down shortly, but the interaction is so strong that you can't see free color, right? What happens is you try to draw off a quark from a proton, say, and you're putting energy into the system, so it creates gluons. Gluons create more gluons, and what happens is you very rapidly, because this force is increasing with distance, because you're just producing this huge number of gluons. The available energy is enough to produce another quark, and so you produce a quark-antiquark pair. Here, draw a sketch of what happens. You've got your proton, two up and a down quark, and so we're going to try to draw off this quark. Okay, so you've got an up quark that you're trying to separate. You've got your up down here, and what happens is, in the midst of this flurry of energy here, one of these gluons pair creates a bar, let's say. And so what happens is you have a meson, let's see, what that would be, like a pi naught here, and you reform the proton over here. So you never get to see a free quark. Now, let's see, then there's this idea of collapsing chair, this idea of asymptotic freedom that, I think this was Wilczek and, oh gosh, I haven't reviewed this. I'm jumping ahead of where I thought I would be right now, because you're most bored by ITEDs. Anyway, they showed asymptotic freedom so that, if you could separate a quark, which would take untold amounts of energy, they would asymptotically be free, not, let's see, what is that really? Sorry. Oh, okay. No, I should review that before I talk about it. But by the early 70s, the consistency of the model was established, that that SU3 color was consistent with what was known and didn't have problems, just manifest problems. Let's see, where do I want to be here? Let me back up to where, let's see, we talked about the Young tableau, the Mesons, charge. Now, electric charge for the Mesons, remember how we set this up, right? We made a plot of, what was it, isospin, the third component of isospin versus what we call hypercharge. These are the diagonal generators of the flavor SU3. And so those are the ones we use to label states. The other generators of SU3 can move us around in this plane. And we find that we generate a diagram like this from the up, down, and strange quarks, let's see, this would be a du bar. This is a dd bar, plus or minus a uu bar. This was a ud bar. And these are identified with the pi naught. Sorry, the pi minus, the pi naught, and the pi plus. There's a second state at the center for the other combination here called the eta, and we found the K naught, the K plus, the K naught bar, and the K minus. The kaons filled out this Meson octet. There's a certain combination here of the hypercharge and I3 that gives you the electric charge. Where did I jot it down here? We could probably infer it easily enough. Yeah, I3 plus I half Y. Okay, so in terms of the coordinates on this chart, as the parameters of the state, you can write a simple expression for the electric charge of each member of the octet. Then let's see. So yeah, I'm just checking my notes. Have you read through this section of the notes?
Which section specifically?
Oh, all right. I'm looking at chapter 13. Have you read chapter 13? That's chapter 13 is flavor. Right. So there's a bit on Young tableau, then the representations of SU3. So we have these raising and lowering operators. The three things I called E that move us this direction or that direction or this direction. So you have 8 generators. These are going to end up being the blue ones, right? So you've got 8 generators for SU3. You divide out 2 as diagonal, and that creates this plane. So you have states everywhere in the plane. The other 6 can be written as 3 pairs, E plus or minus. And those act just like the raising and lowering operators for the spin. Where last time at the end we talked about the different spin states and Clebsch-Gordon coefficients and all that stuff, right? These do just the same thing. So yeah, that's where we left off last time, talking about Clebsch-Gordon coefficients, right? You guys got that, I think. That's clear. Okay, so the other 6 generators are just like J plus and J minus, but you've got 3 pairs of those. And so one of them that I call E12 changes the Z component devices spin. It moves you E12 plus moves you this way, E12 minus moves you that way in this diagram. So from one combination of quarks to another. Notice if you step, let's see, this is going to be probably a strange. No, wait a minute. D. Hang on. Yeah, if D goes to S. Bar, no, this has got to be a D. Can't be a DD bar, S bar, DS bar. Yeah, so U bar goes to S bar, and then this is going to be US bar, which is positively charged. Okay, and then this is going to be a D bar S, and this is going to be a let's see, U bar S. So strange quarks, anti-strange quarks. You can move from one node to another by by changing one quark. So to go from pi minus to pi naught, you can either change a D to a U, or you can change a U bar to a D bar. And basically that's how you get this combination. If you apply that same isospin raising operator again, you're going to change a D to a U and get a UD bar, or here you can change a U bar to a D bar, and that also gives you D bar. So just applying those operators, like raising and lowering operators, you move step by step through this diagram. To move this direction, right, that's each of those involves a change in the hypercharge. Hypercharge because you don't know what it is, but it acts like a charge, right? It's a measurable thing, right? It's like electric charge, but now it's some other sort of quantum charge. And if you apply right, one of the 2E's, it will take, this takes a, what do we do? A U bar to an S bar, or it'll take, wait a minute, yeah, it'll take an S to a U, or it'll take a U bar to an S bar. You always have the option for the inverse. So if you're looking here, it can take, what did I just say? A U bar to an S bar, an S to a U gives you this U bar. A U bar to an S bar takes you a step further to the US bar. Right, so you can figure out what quark each of these raising and lowering operators changes, and you trace out the possible states. Now, this explains, these actually are the lowest mass mesons. We see all those. We saw them early on. We saw them, 50, 60 years ago. But what has happened since is you see excited states of these things. So, rather than this whole panoply of new particles, people have systematized the notation for all these particles, and you'll find these labels iterated at higher and higher energy. So if you go to the particle theta group pages, you'll see a particle name like Psi or Delta that lies in the Baryon Octet we'll look at in a minute. And it'll have that same name. It's an excited state of that particle, and it decays very quickly down to either the regular corresponding baryon, or often into mesons and maybe proton. Let's see. This is, all right. I think I laid this out pretty carefully in chapter 13. So, read chapter 13 and see if you have any questions about it. I go through details that, there are a lot of ways of looking at this picture. One thing you can do is, let me mention this. Right, these things are matrices, right? So we can be more concrete about what these operators look like. So just like the SU2 matrices, we have, say, E12 plus or minus are given in terms of these Galvan matrices, lambda 1 plus or minus I, lambda 2. just like J plus or J minus. And what that looks like is a matrix, right? These look like, they look like SU2, but they're 3 by 3. So they have either plus or minus I off diagonal or ones off diagonal, a pair of ones. But when you take this combination, you get something that has, say, a 0 has a 1 in one position. So I call this E12 plus or minus. The minus one would have the 1 down here. And so from those Galvan matrices, all right, that's a basis for the Lie algebra of SU3. We diagonalize 2, I3 and Y. And then we form 3 combinations like this with the one here, here, and here, or on the opposite side. If the one's up here, it's a raising operator. This is going to act on UDS. So what this is going to do is it's going to, whatever's in that second position is going to appear up here in the first position. So basically, you're advancing this D up to the U position. Whatever field is here becomes the field up here. You've changed the D quark into a U quark. So these generators are moving your triples around quite explicitly. This is a graphical representation of it. You can do this with Young tableau. You can maybe that's the thing that gets confusing about this is that there's so many different ways to look at what we're doing. Young tableau and these plotted diagrams and the explicit matrices, but these are all describing the same thing. These are all describing the states of multi-quark systems. So you guys are awfully quiet. Is there a question I can answer? Is it confusing or trivial? You're good? Okay. Kevin, you good? All right. Okay, so let's move on. Do the same thing with the baryons, and then we can dig into the standard model a bit. All right, so when you get to baryons, it turns out, this marks really well, but it doesn't unmark very well. Oh, geez. Wrong marker to be using. Let me just. Yeah, what a mess. You have to compute the charge a slightly different way. And what you find with the baryons is that you actually have different quantum numbers associated with the different quarks. Let's use that one. So we have up, down, strange, charmed, top, bottom quarks. We have all these quarks, and nature can tell which quark we have. So, these individual properties are conserved by strong interactions. Let's see. So, there are quantum numbers S, C, T, B called strangeness, charm, topness, and bottomness. which are very weird words to use, but those are the names of these charges. And so strangeness is actually the number of anti-S quarks minus the number of S quarks. Charm is the number of charm quarks minus the number of anti-charm. Yeah, the strangeness and bottomness have a different sign. The sign convention is flipped. So here again, we have the number of anti-bottom quarks minus the number of bottom quarks. Here we have the number of top quarks minus the number of anti-top quarks. And the charge is a combination of all of these quantum numbers. There's another quantum number, B. This is B prime. B is a quark number. And that's 1/3 per quark, for each quark. You know, I'm realizing part of what the problem is here. You didn't know there was a problem. I know you guys get this, but the
You solved it. You solved the universe. No.
yeah, we've done it. We've done it. The point is that the standard model, and all of this this group theory stuff has been developed to describe stuff that nobody knows shit about, right? Like people don't know about delta plus plus particles. So when you when you say, okay, the quark model explains the delta plus plus and the omega minus and the all of these different the sigma triplet and sigma star triplet, like what are those? You've never heard of those before. So there's this whole mechanism that's developed to explain things that nobody, not even graduate physics students, have heard of. Like what's with that? Well, you need to have heard about this stuff. You've heard of atoms, right? So when you study quantum mechanics and develop this strange formalism, you at least know that, oh, well, all right, I know what hydrogen is. And so, it's pretty immediate. We're talking about stuff that is, at 10 to the 10th times smaller than atoms. And this has been very well studied for, since at least going back into the 50s. When was the neutron discovered? 32 or something. This stuff isn't that old. And so developing this whole formalism of group theory to understand fundamental particle physics, you really need to be a little deeper steeped in what particle physics is talking about before you can really appreciate what has been accomplished. Have you guys gone to the particle group data pages?
I think in my undergrad they gave us like a pack, and it was like this thick of just a bunch of sheets. And it was literally just to show us how big these data sets can be of just information.
Oh. Yeah, okay.
It was just an emotional response to give us, but I guess it worked.
Yeah, okay. Well, there's that. Here, I'm gonna share my screen here because on this computer I actually know how to do that. And if I can find you guys, here we go. Okay, so let me view over that way and this over that way. And now, how do I share the screen? Here, share the screen. Okay, so are you seeing my screen.
Yep.
And then, yeah, all right. So this is part of the particle data group pages. Might make sense to go back to the home page. Is this the home page? Yeah, particle data group. That's what it's called. Fine. Okay, so this is the home page of the particle data group. This is a government coalition that I think forget where it's run. It might be run out of Cornell now, either Cornell or Lawrence Berkeley. But this is updated continually. If you want the current data on particles, this is where you go. Absolutely, irrevocably, this is it. So if we go to, say, the summary tables, let's see, there's actually summary tables, article listings. Yeah, well, I'm not finding this right away, but okay, suppose you're curious about the Higgs particle, big news, right? So gauge and Higgs bosons, okay, this also includes the W and the Z, right? Decay modes, right? A Z particle decays in 20 different ways. And most of the time, let's see, well, 69% of the time here, it decays into hadrons. If you can see this line. So almost 70% of the time, it decays into hadrons. Well, these are the various hadrons it decays into. So that's broken down further. But this kind of data, oh, whoops, more like 40 than 20. Here's the Higgs, all right? And signal strengths, all kinds of information about the Higgs. What I found really interesting when I first came to the Higgs page, this doesn't have it. Where does it? Right, there's rats. Yeah, navigating this stuff. Right, particle listings. Here we go. Searches for the Higgs. This is fascinating because there have been so many searches for the Higgs. These tables list every experiment, every credible experiment, right? Starting with 1 through 4 here. Let's see. The search. What was done, references, and this list of searches for the Higgs goes on and on and on. All of the measurements that anybody has ever done over 50 years, none of these actually saw the Higgs until 2000, what was it, 12, 14, whenever it was. But what they did do was put limits on the mass range. I'm still strolling through searches for the Higgs. This is a lot of experiments at a lot of different accelerators. I don't know how far is this guy? I'm halfway through here. This is still Higgs searches, Higgs searches, Higgs searches. These tables have everything, right? And oh, geez, what is that list? Here, let me look. Yeah, searches for neutral Higgs bosons. These are the references to the searches. A's, there are the A's. Well, you get the idea. If we go back to summary tables, and we want to know, okay, here are the mesons. So we, the light unflavored mesons, these are the ones built out of just U and D quarks. And so we have the pi plus or minus here. And then here we have the pi naught. And you can, again, a lot of effort goes into getting the branching ratios. 90% of the time, a pi naught decays into 2 photons. Then the rest of the time, you get, any of these. It can, 2 electrons and 2 positrons, or electron-positron pair, or 4 gammas, or neutrino, antineutrino, and so on. Here's the eta particle, mass about half the mass of the proton, here, there, and decay parameters. They have, what else? Decay, they have, let me see, did they give the, oh, okay, this full width. All right, I believe I talked about these decay peaks, resonance peaks. Back when we were looking at cross sections, I discussed resonance peaks, and these peaks have a certain width that is characteristic. From the width of that little peak, you can tell about how fast the particle decays. Basically, h bar over the width of the peak tells you what the half-life is, or the characteristic time. So the data tables quote that as the full width of the resonance peak, not as the decay time, but those are directly related. And then they give the mass. This notation here, you may have seen this kind of notation for atomic states. They use the same notation for particle states. So J is the total spin, parity, charge conjugation, this minus plus for this particle. Isospin and G are new ones, but they measure those. So then we get into some new particles, F naught, rho, omega, eta prime. I don't know all of these, right? This is a lot of particles. If you're really, you're working in an accelerator, you're building the thing, or you're building models to work out details of the standard model. It's a work in progress still. There are some mysteries. It's not what you hear about every day, but you get some of the online chats about this kind of thing, and people are saying, well, how about the F2 1270? Actually, I think that one was mentioned. Something, the 1270 cents. It's an odd state. It's not the kind of state that you would have predicted just from the Young tableau or the raising and lowering operators. There's something else going on there that is a little anomalous. Or, they even have, maybe at the end here, let me see, they save it for the end, but there are, strange, now we're going to add the strange quark. All right, well, see, this goes on forever, right? So I don't need to drag you through all that. And all this has references, of course. But I think these last particles may be exotic states that just don't fall into the standard quark picture. But, you get things like glue balls, right? Bound states, quasi-particle states, they decay, but of gluons. Gluons can beget and interact with other gluons, and so you have what are called glue balls. This is the data that the standard model explains. Who's ever seen all this stuff, right? It's here, and I want you, particle data group. if you ever want to know anything about particles, it's here. Particle data group. And well, let's see, let's not just scroll back through all of that. Anything here you want to see? Let's, here, we can take a look at the baryons. All right, S equals 0. So no strange quarks. We're just looking at up, up, down, or just up and down quarks. And we're talking about baryons here. Notice they're called N baryons. That's for nucleon. These are sort of the different states of the same thing. You're just flipping the isospin for an up-down quark pair. So, the positively charged nucleon is the proton, and it decays. Well, it doesn't decay. It's never been seen to decay. I think the constraints on the proton life are, there are different studies. One place is different kinds of experiment that put limits on the proton lifetime of 10 to the 31 years, or there's one that says 10 to the 33 years. And, neither has ever seen a proton decay. It's quite possible it would decay at some point. Most unifying theories, including string theory, end up predicting additional particles that we haven't seen. And those include particles that would allow direct decay of quarks into leptons. And the limits on that occurring are very strong, because if a quark can decay into a lepton, then a proton is not a stable particle, but will decay into electrons or positrons and neutrinos, whatever. The limits on the lifetime have to be, have to allow your model. So if you want to build a unified model of everything, your TOE, your theory of everything, you had better not predict proton decay any faster than 10 to the 31 or 10 to the 33 years, or else you're already in conflict with data. Now, Witten showed a decade or two ago that there exist string models where the proton lifetime is greater than 10 to the 35th years. Hence, there are string models that are consistent with the observations of non-proton decay, but they do predict proton decay eventually. Okay, so question for you guys: how do you show that the proton lifetime is 10 to the greater than 10 to the 30 years?
Get a lot of protons.
Yeah, that's right. Exactly. Yeah, here, let me stop this share so I can see you guys better. Yeah, you get a lot of protons, right? Super Kamiokande. You've seen pictures of that, right? I'll pull one up if you haven't, but you know what that's like. It's this huge tank of water. It's got a lot of protons in it. So you look at enough protons with sensitive enough detectors, and if a proton were to decay in that tank, it's a very energetic decay. Proton's got a lot of energy. It's going to decay into, well, perhaps electrons, right? Positrons. Those are going to be moving really, really fast, and they're going to send off a lot of Cherenkov radiation, and that will be picked up by all the photodetectors around that huge tank of water. Are you familiar with what I'm talking about? You've seen this? So tank with a little lifeboat out in the middle of it, and all these photodetectors all around the perimeter, huge tank of ultra pure water. And I don't know how they get the barnacles off the boat, but those photodetectors will see Cherenkov radiation in a discernible spot, with its measurable energies if a proton decays in that tank. So you can put really stringent limits on proton decay. All right. Yeah.
Any worthwhile results from that, or have they?
All right. So let's see. Let me. Proton decay. I'm just going to Google it here because that's what you do, right? Let me see if I come up with something. Super Kamiokande limits on proton decay results with about 300 kiloton tons of water, a year of data. We could not find any candidates for proton decaying into positron or neutral pion, and we set a lower lifetime limit of the proton as greater than 1.6 times 10 to the 34th years. So that's the latest from Super Kamiokande on proton decay. Now, they look for specific decays, and presumably they're looking at what by the standard model, you know, by what we know about the strong interaction or unifying theories, it should be expected to be the principal mode of decay. You know, until you see it, you don't know for sure what the most probable decay mode is. But what are they looking at? A positron and a neutral pion. Well, you know, if it's going to decay into, you know, produce a lepton, it's, you know, it's not going to be an electron. It's going to be a positron. You know, it's charged, so the charge is going to go with the lepton. And, you know, what's going to be left over? Well, really, what you're looking at is a quark decaying into a lepton. All right, that's what is predicted by any fundamental model that that allows proton decay. Let me give you an example. You want to see an example of a unified model that predicts proton decay? Let's draw a picture here. So, all right, you know the standard model, 2 cross U1. We're going to get into detail on this. So this is electroweak, and this is color. So these are the symmetries. You would like to find some unifying group symmetry that actually predicts this. If you look at SU5, the generators of SU5, all right, are we can write as 5 by 5 matrices, and in this upper corner, we can fit an SU3, and in this lower corner, we can fit an SU2. So within SU5, we have a direct product of SU3 and SU2, but notice matrix 1, 1, 1 minus, the generators have to be traceless because it's a special unitary group. But if you take, wait a minute, minus this 3, minus, what do I want here? How do I make this traceless? 3 minus half of 3 halves. How about minus 3 halves? Minus 3 halves. Okay, that's one way to do it. Okay, that's a traceless. That is a generator of SU5, right? It's traceless. It's Hermitian, so it's one of the generators. But notice it commutes with the SU3 and the SU2. So this can generate a U1. So within SU5, you have all the symmetries of the standard model. But you've got other stuff as well. These are called X particles here. These are called Y particles. And then conjugates over here, I think you've got X bars, you know, minus X stuff. But you're predicting 6 new particles. Now, these act on triples of quarks. The SU3 acts on triples of quarks. The SU2 acts on leptons and couples them to other similar things, you know, over here, Q, 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 L, L. But these objects, all right, if you multiply this in, you're going to have a lepton with an X particle, and then that's going to hit a quark. So something like this, where you've got some big fermion multiplets here, psi bar, an interaction term with SU5. This is like what we did with electromagnetism already. Remember the vector potential with a gamma matrix, and we had psi bar. We had something like this for the interaction that came from gauging U1 to get electromagnetism. You do the same thing here, and you have a psi bar, and you have some gauge field that is a Lie algebra valued object. And so you're putting in a direct coupling between a lepton and a quark. This will allow the decay of that quark into that lepton. So from the kinds of term you put in the action, you know what interactions, what decays to predict. And this unified model very neatly contains the standard model, but unfortunately, given the constraints that you actually get from experiments, that puts limits on how big masses can be. You want these things to be really massive so you don't see them all the time. You've got to really suppress the decay of the proton, but you can only suppress it to about 10 to the 31 years, and that's ruled out by experiment. So this model does not work. It fails as a unified theory because it predicts proton decay in 10 to the 31 years, and we know protons are more stable than that. So, that's the kind of thing that happens in unified models. There are some real limits on what you can do with a unified model. I talk about this in the introduction to the standard model picture, but I got to post that in the next couple of days. There's an important theorem when it comes to unification. In the 1970s, gosh, we're talking like 50 years ago now, but there was a huge amount of work on what were called grand unified theories, GUT. And these grand unified theories were models like this, or SO10. SO10 might work better. Modified versions of this can work. But people posited all sorts of groups, conformal group, or just, SO, any orthogonal group, or any unitary group, SUN with n bigger than 5 can contain the standard model. So nobody had any guidance at all about what sort of unification, what sort of unifying groups you could choose to see the unity, right? We have two really effective unifications in the history of physics: the unification of electricity and magnetism in the Faraday tensor, and the unification of the electromagnetic and weak interactions, which we're going to talk about in detail over the next few weeks. You would like to see that kind of unification where these things are realized as different aspects of a single kind of interaction. But there are some limits to it. The most stringent limit, well, okay, there were really two problems. One problem is you don't know what bigger group to choose. You can choose anything with no guidance. The other problem is if you try to include gravity in your unified theory. Now, grand unified theories were aimed at accomplishing the standard model within one symmetry. But people also tried to bring gravity into the picture. And that meant that for gravity, you start with the Poincare group. The Poincare group is the Lorentz group plus translations. So it's the space-time symmetry. And so what you'd really like is something that includes SU3 and SU2 and U1 and also the Poincare group. But there's a theorem, the McDowell-Mansuri theorem. McDowell-Mansuri showed that if you ask for a unified theory that includes gravity and the other interactions, and which satisfies, they had about 4 basic properties that any reasonable quantum field theory could be expected to satisfy, could be required to satisfy. They showed that the only way to do that with the Poincare group and some internal symmetry, these symmetries are called internal, they're not space-time symmetries, they're some other symmetry. They showed that you can't do it. That the group must be a direct product of the Poincare group and some internal symmetry group. And that's pretty much a no-go theorem. You can't unify gravity with the standard model without doing something different. You can't just find one group that does it. Well, that was the early 70s, and that was when supersymmetry came to the fore, because supersymmetry avoids that theorem, right? McDowell-Mansuri were looking at Lie groups, and with a graded Lie algebra, that allows anti-commutators and not just commutators in the Lie algebra structure. So you extend this to a super Lie algebra, which mathematicians, quickly called physicists, would be called a graded Lie algebra. You suddenly can have some non-trivial coupling to translations. You have this supersymmetry that relates different spin particles of different spin. And those transformations have an anti-commutation relation that gives a translation. So they're a direct coupling between a particle symmetry mixing spins and the translational symmetry of space-time. So you do get a group that is a supersymmetry group that couples gravity and the other sectors. And so based on that, up into the early 80s, there was a lot of work on supergravity theories. So in a supergravity theory, you have general relativity, but you also have a symmetry that mixes that with lower values of spin 3/2, spin 1, spin 1/2, and scalars, in definite proportions. And so you start writing a model with a superfield that describes not just general relativity, but a bunch of spin 1 particles, spin 1/2 particles that is capable of encompassing the whole the whole gamut of known interactions. Theories of that type are called TOE, T-O-E, theory of everything. So even better than a gut is a TOE. You've written some supersymmetry that can predict the interactions of not only gravitons, but also the internal symmetries of the standard model. Now, those had the same, still have the problem of, what group do you choose? How do you specify, do you take, supersymmetric, SO97? It could be anything. You don't have any guidance. The guidance came from another direction, right? In the late 60s, Nambu and I think it was a student Goto were working on a model of mesons. The idea was that the force between two mesons is very strong. So in some sort of classical picture, the lines of force are very tightly combined. So you've got more or less an extended object along one dimension that approximates what a meson is. And so they looked at a string theory, right? They described a bit of string with some charges on each end. Those would be the mesons, some quantum numbers on the ends. And they can spin and do all sorts of things. And they have energy modes because the string will oscillate in various modes. And the idea is that, different oscillations are going to give rise to different mass. And so you can generate a spectrum of the different mesons. And they did that. And it gave a sort of theory of mesons, but what seemed like a problem for describing mesons seemed like a real advantage to John Shirk and Joel Shirk and John Schwartz. Shirk and Schwartz recognized that a spin 2 mode is what you would expect for a graviton. And so they started to work on a string theory of gravity. And by 1976, they showed that if you look at the massless spin 2 mode of string as an effective field theory, that effective field theory is general relativity. And it more or less had to be because they could show that the symmetry of string contains the Poincare symmetry. So you would expect that right off. And that conclusion was confirmed in various ways. So now you have two lines of investigation. You have people doing supergravity theories, and you have Shirk and Schwartz doing string theory. People didn't jump onto the string theory idea for gravity for a while. That wasn't until 1984. At that time, Green had started working with Schwartz. Shirk committed suicide. He was disappointed that no one was picking up on string theory. He was convinced that it was the way to go. So after that, Schwartz started working with Green. And by 1984, Green and Schwartz had gotten a result about the internal symmetry associated with a gravitating string that, let's see what's now. Is this a superstring? They probably supersymmetrized the string. And what they showed is that when you supersymmetrize it, what they found was a unique symmetry group, SO32, which is easily big enough to contain a standard model. But as of Christmas 1984, the it was known that there was a almost unique symmetry group that arises inside of string theory. They were going to a conference to announce this result. They called Ed Witten, and he observed that they were going off the number of generators of the group. They calculated the dimension of the group, and it turns out there are actually two groups that have, like, I don't know, 512 generators or 252 generators, some huge number of generators. Yeah, I think it's something like 512. E8 cross E8 or SO32 are the only two groups that arise from string symmetry as the internal symmetries for the particle model. And so in the winter of 1984, after that announcement, about 1,000 theoretical researchers shifted from doing supergravity theories to doing superstring theories. And since then, string theory has been more or less the standard the standard theory of everything in the thinking of particle theory. So you have a concrete prediction of one of two possible internal symmetry groups. You have a model that's known to give general relativity to parts in something like 10 to the 60th or something. There are corrections to general relativity from string theory, but they're suppressed by the Planck length squared. So, the second order gravity terms don't come in, they have a coefficient that's like 10 to the minus 60th. And so indiscernible difference from general relativity, unless there's some really interesting properties that arise from the higher order terms. It's was shown to be consistent with non-decay of the proton at a sufficiently high level. Various models were developed to account for details of the standard model from string theory, and that's still ongoing. I don't know, either of you guys know Laura Anderson? She got her PhD here. No, I'm sorry, a master's degree here, but then went on to, let's see, where did she study? I think she went to Princeton. Yeah, she was at Princeton. You know the archive, right? All right. Well, she, one of her jobs at Princeton, and this would have been, oh wait, no, I'm sorry, I'm confusing her with something else. No, what Laura has worked on steadily is working with large classes of compactification of 10-dimensional string theory down to the 4-dimensional models with 6-dimensional compact manifolds at very small scale. You understand how compactification works? It's sort of, okay, so, picture the difference between a 2-dimensional plane and a garden hose. Okay, they're both 2-dimensional surfaces, but the garden hose looks like a line, right? You get far enough away from it, you don't see that there's a circle there, right? That's the idea of compactification, that the first compactified model was Collusion-Klein back in the 1920s. They modified general relativity by adding a 5th dimension, but supposing that it was compactified on a circle of very small diameter, sufficiently small that it would not have been measured. And so what you do is you do Fourier modes on that circle, and you keep the lowest mode, basically. So now all your fields only depend on the other 4 coordinates. But you do have this internal U1 symmetry, which could be electromagnetism. And so the Kaluza-Klein model, the original Kaluza-Klein model, was a unification of general relativity and electromagnetism. It's successful. It's a plausible model, except that we know there are other interactions. But Kaluza-Klein theory really came into its own, in the 60s and 70s, where people were exploring higher dimensional models when they're doing supergravity theories. So you supersymmetrize general relativity, you get some internal symmetry. People talked about maximal supersymmetry. You can have an 11-dimensional supersymmetric theory, and that's what people worked with because it was the biggest one you could write, that where the highest spin was spin 2 for the graviton. We don't see any spin 3 particles. So, it puts a limit on how high, how much supersymmetry you want to include, and that restricts the dimension. So if you do a supergravity theory in 11 dimensions, now you just need to come up with a way of compactifying 7 dimensions, a la Kaluza-Klein. So you're going to take 7 dimensions and roll them up in some kind of sphere or a couple of spheres or some compact small manifold, sufficiently small that we don't really see it except for that residual symmetry. You use that residual symmetry as an internal symmetry for your standard model, and you end up with what looks macroscopically like 4 dimensions, but actually you have this internal geometry going on at each point that is giving you additional properties that you don't know enough about other than to call them color or flavor or something. So you build models this way. So that's the idea of compactification. Well, string theory turns out to really prefer certain dimensions. If you're talking about a bosonic string, one of the things you must have for a successful string theory of gravity is the Poincare Lie algebra. This is something cool. I want to talk about string theory in some detail after we do the standard one. But you have string modes, right? It oscillates. It's got a definite length, and you get a certain spectrum of oscillations possible on a bit of string. And those, those are really different particle states because we're talking really high energy here. Now you quantize the string, and it's a lot like quantizing a particle. For each of those modes, the amplitude becomes an operator. And it's just like the quantizations we did early in the last semester. But now you've got all of, for each integer, for each mode of the string, you've got an operator. And it turns out there are certain binary combinations of those, quadratic combinations of those mode amplitude operators that satisfy something very much like the Lie algebra of the Poincare group. So here you have a quantum system that where the quantum operators generate the symmetry of gravity. That's compelling. And I don't know any place else that actually occurs. But there's a glitch because there's this extra term. It's called a central charge, but there's one extra term in the Lie algebra you make from these mode amplitudes. And that term has a coefficient of essentially the dimension of the space minus 26, which means that if you choose to work with string theory in 26 dimensions, then you have exactly the Poincare algebra, and it will definitely generate general relativity. All right, so now what do? You've got this higher dimensional theory that's giving you general relativity. Well, that's called the critical dimension. If you supersymmetrize string theory, it turns out that that critical dimension drops to 10. So superstring theory really, in order to have exactly general relativity, is going to have it's going to start in 10 dimensions. So you need to compactify 6, and there's a huge amount of work going into classifying 6-dimensional compact manifolds. And so Laura Anderson from USU has spent most of her professional career looking at classifying 6-dimensional compact manifolds, for that reason, to find well, and with the criterion that what's left should look like the standard model. So there are some constraints on what that this manifolds can be. So anyway, here I am just rambling about string theory. We're getting way ahead of standard model. Let's see, and I didn't talk at all about Baryon octets. Let me see just a second here what I want to say about baryons. I started, yeah, let me quickly run through the Baryon octet, and then we'll be in a position to really start writing things down for the standard model. So the charge operator depends on all of these. So when you start talking about baryons, we have all of these different clone numbers, and so you can write the charge of any given particle as you still have the third component of the isospin, but then you add a half of everything else inside. So the baryon number, the strangeness, the charm, the topness, and the bottomness all contribute to the electric charge. Yeah, that's it. So this is the way we compute the charges once we know the quark content of any field. Now, if we look at up and down quarks only, move this out of the way. Baryons, and this was not understood until color symmetry was seen, because remember why people posited color in the first place. You needed to make the wave function anti-symmetric, and for some states that otherwise could only be symmetric. Now, an anti-symmetric configuration of 3 quarks is it's a singlet state, right? There's just this one anti-symmetrization. So if you have a red, green, and a blue quark, there are only 2 ways that you're going to get singlets, or well, at low enough energy, there are only 2 ways to end up with the singlet state. One is you take a color and an anti-color, right? That has no net color, and it is a singlet. The other possibility is to take one of each color, and that also is a color singlet. You can anti-symmetrize those. All right, well, you know what these are. These are the baryons, these are the mesons. And quantum chromodynamics predicts that those are exactly the quark combinations we should see. You might also think, well, what if you took red, green, blue, together with a red anti-red. That would be some sort of pentaquark. Well, these have just been seen at CERN, right? They're seeing some of these higher things. They've got enough energy to, for a very short time, produce one of these. Hope we haven't lost Guillermo here. It's actually further evidence for for quantum chromodynamics that you actually do see these at sufficiently high energy. The baryons. Suppose we go back to flavor symmetry, and we're talking about the up, down, and strange quarks, and so precursor to to color, but one in which we do expect to see either mesons, quark antiquark pairs, or quark triples. And that prediction, as I said, comes out of color symmetry, but it was recognized earlier that you need these kinds of combinations in order to account for the lightest mesons and baryons. So we looked at the mesons. Let's look at the baryons. And suppose we just look at the up and down quarks first. What are the possible triples of up and down quarks? So here we're looking at basically Young tableau 2 by 2 by 2. Sorry. So if we have 3 quarks and want to know the combinations of 3 quarks we can make, it's going to be this, which is a 2 times, right? These can be either symmetric 2, 3, or anti-symmetric 2, 1. And if I bring in another quark, then we can have 2, 3, 4, or we can put this below, so we have 2, 3, and then 1 below. Or we can do similar things with this one. So there's another 2, 1 where we symmetrize the next one, or we can totally anti-symmetrize and we get a singlet. But you can't anti-symmetrize a triple of 2 quarks. So this one's not going to occur. You get a 0 here. Okay, so what is the multiplicity of these? Well, for this one, we have 2 times 3 times 4 divided by 1 times 2 times 3. That's a quartet. These, let's see, we have 3 times 2 times 1 is 6 divided by 1 times 3 times 2. That's a doublet. So we expect a mixed symmetry doublet or a totally symmetric quartet. And this is all out of just U and D quarks. So we know how to generate these things using the raising and lowering operators. Those are still the same as they were. So we could start with, for the symmetric set of 4, we could start with 3 up quarks, and then we can apply the UD, what is it, E12 takes a U to a D or D to a U. Let's see, the -1 takes U's to D's. So here you're going to get a UUD and a UDD and a DDD. You get four particles, and This one is identified with delta plus plus. Now, did you know that there was a fundamental baryon with 2 positive charges? Delta plus plus. There is. All right. This one, D is minus a third, so this is 4/3 minus a third is, we call all of these deltas. This just lowers the charge by 1 each time, and the DDD has a charge minus 1. So we have a quartet of what are called delta particles that comprise this totally symmetric combination. Then we have a mixed symmetry doublet. There are 2 of those. When you include spin in these models, you know, these are still approximate, but when you include spin in these models, you find that we really only want to look at one of these doublets. So you have a UUD orthogonal to this state, where you're basically able to anti-symmetrize the UD pair, one of the UD pairs. And then you can have one U and 2 Ds, UD and another D. And this has charge +1. That's the positively charged nucleon, and this is neutral. And of course, these are the ones you identify with the proton and the neutron. So this mixed symmetry doublet under SU2, we identify with the proton and the neutron. That was the pairing that initially led to all of this, right? The idea that the proton and neutron are so close in mass, they must be 2 states of one kind of particle. And, at this point, we know of dozens of N particles, various excited states of these same quark combinations, as well as strange versions and charm versions and so on. Now, that's just looking at U and D. If we look at all 3, now we're going to take 3 by 3 by 3. And that gives much the same thing. We get a totally symmetric 3, 4, 5. We're going to get 2. It's the same boxes, but different numbers. 3, 4, 2, and we get another one of those. And we get a singlet state, 3, 2, 1, like this. So there's one of these. All right, these 3 times 4 times 2 over 1 times 3 times 1 is 8. So each of these is an octet. And this 3 times 4 times 5 over 1 times 2 times 3 is 10. This is a decaplet. So with spin, we only count one of these, but we expect to see a decaplet, an octet, and a singlet state for the baryons built from UD and S quarks. Now, it turns out you don't actually expect to see this singlet state. Right? That's anti-symmetric, but if you have a symmetric ground state, right, the spins of the quarks have spin 1/2, and so the spin state for 3 quarks with if they all add symmetrically, you're going to have a spin 3/2 particle, which is symmetric. This is a totally anti-symmetric wave function I'm getting something backwards. It's in the text. Read the book. Yeah, I think the quark state is antisymmetric. The spin state is symmetric. So the spatial state would have to be antisymmetric. So you can't get a symmetric ground state. So you don't really expect to see this particle. That's the upshot. The symmetry doesn't work out for this particle to have a ground state. You only see excited versions of that state. And so the things that you have relatively stable ground states, you expect a decaplet and an octet. Well, if you start adding S states to this fourplet, you're gonna get the decaplet. And the proton and neutron give you the octet. So we've got EED. We have the delta particles here, delta minus, delta plus plus. But now the other operators take us in these directions. You can't. There's no place to go in this direction from DDD or UUU. You can't increase. You just get zero. But you can generate a triplet of states here, like this. And I think, are those called, what are those called? I forget. See, nobody talks about these particles. So we include this range quark and, sigma star. Yeah, I thought it was sigma something. These are called sigma star. And what's the charge of this? So we have up, down, down here. So if we change it down to a strange, we're going to have SDD. So each of those has minus 1/3 charge. So this is -1. And as you move to the right, the charge goes up by 1. So you get a sigma star naught and a sigma star plus. And you can go down again. Either route, there are several routes to going down here. And what you get at the next level are called psi particles. And you go one last step and you've got the decaplet. So these are psi. Now, this operation gives us a doubly strange with a D that's still a -1. And this is going to be neutral. And then you come down here and you get an omega particle, which is triply strange. 3s quarks. This particle is the one that led to the initial postulation of an extra quantum number, the quantum number of color. Looking at the wave function, the spin, and the quark content, the symmetry of this always comes out positive, and yet it's supposed to be a fermion, so it has to be negative. So you're pressed toward the conclusion that there must be another quantum number that you can anti-symmetrize, because they see the particle that's got the required spin and other properties, but it doesn't have the right anti-symmetry. So that's the decaplet. Then from the proton and neutron, you get an octet. So here, now we can go both ways because we actually, if we can change any of these particles either way. So you can apply either of the S raising operators to these states. So you can go either direction with your raising operators. So here you're going to get Oh gosh, let me think which way we go here. I better look. Yeah, all right. This you have a U here to change to an S, so you can get an SDD here. If you change a D to an S, you're going to have something like a USD here, which can occur, and you can anti-symmetrize this 3 different ways. So there are a bunch of states possible here, and then here you're going to have a US, and moving this way, you're changing D's to U's, so this would give an SDU. So various combinations of one each of the different quarks can be at the center. There are, the totally anti-symmetric state here would be the singlet state, but there are 2 independent states here. What are they? Well, these are the sigma baryons. This is the sigma minus, the sigma naught, and the sigma plus, and the extra state here is called omega. And then we can turn it down to an S, so we have an SSD. There have to be at least 2 quarks here, or you can't anti-symmetrize. And then you can come this way, and this is going to be an SSU particle. And those are called, forget, what are those called? Xi. Those are Xi particles. This is a Xi, that's going to be minus. This is 2/3 minus 1/3 twice is Xi naught. And we've filled out the Baryon Octet. So those are the lightest expected baryons. Now, what has been seen since, people started seeing other particles beyond these. And they were similar in quark content. And it was finally realized that they're excited states of these particles. That was not immediately obvious. Can you tell me why? Why wouldn't it be clear that you're looking at an excited state of the proton? All right, well, the masses were very different. If you have a bound state of quarks and you excite one to a different orbital, okay, an atom, you excite an electron, you go up a few electron volts. What's the mass of an atom? Well, it's the mass of the proton. But the mass of a quark, the U quark has a mass of maybe 2 MeV. That proton has a mass of 1,000 MeV, right? The energy is all gluons and kinetic energy. The mass of the proton is all interaction energy of the quarks and gluons. A very small part of it is the mass of the quarks. If you bump those quarks to a higher energy state, you could be adding GeV, you're certainly adding many MeV. And so the mass of the resulting particle is going to be substantially different than the mass of the proton. So it wasn't clear at first that you were looking at just, nucleons with some more energetic wave functions. But it turns out, and the naming, let me see if I've got this naming. Yeah, this is 13.8. Here, I might as well share the screen. I can just show you this. The naming, I have too many things open. All right, here. So baryons with any number of U and or D quarks are nucleons. they're denoted by N. Or if they're excited states of the decaplet, they're delta particles. So let's see, I don't know, can you still see the board there? So the U and D quarks gave either the proton and neutron, or they gave the 4 delta particles. And so any particle with that same combination and symmetry of quarks is either a nucleon or a delta, but excited states. So they keep the names from this octet and decaplet all the way to higher energies. And so if it's got a single, two U and or Ds, well, what else can you have? Well, you can have an S like in these, but you could also have a charm or top or bottom quark, one supposes naively. And so you put a subscript for S, C, B, or T, depending on what that third quark is. And then you can have 2 remaining quarks, and so on. So you exhaust here the various number of U and D quarks in the naming, and that gives you a consistent way to give the name of everything. Now, most of these higher states are very short-lived. They decay very quickly, probably emitting mesons or something. They decay down into lighter baryons, with the proton being the final stable state. So for the things that rapidly decay, you have a notation like this, where in parentheses after the name, you give the mass. And things with the mass denoted that way are not very stable. They decay very quickly into the lighter baryons. So, and then, for mesons, there's a naming scheme too. I put a link to the particle data group pages here. Probably the one where this naming is laid out. You can read there about the mesons as well. Oh no, this just goes to, I thought I was linking to the particle listings. There's, well, no matter. Whoops, what have I done now? And no, here. And you can add more quarks and you get all these same names. Which, you will be pleased to hear. How much time have we got? There, I'm going to share this again. Because that's the end of the chapter, and the next chapter is the standard model. And I think I've already talked through a great deal of this. This first section is all history. And I have gone through a lot of that with you. So we're ready to talk about really constructing the standard model. So you see how we got here. How are you guys holding up? I'm going to start laying this out. You're good? Okay, good. So we realized by, say, the early 70s, 1970, maybe late 60s, after Wilczek and others, the quark model is on firm footing with SU3 color as the symmetry that gives rise to these combinations, and predicts the fact that we're going to have either combinations of quark anti-quark to have 0 net color, or of red, green, blue, one of each color, like blending all colors makes white, right, is the idea. So you have a color singlet, which is going to be your lowest energy color state in mesons and baryons and pentaquarks, you don't see free color. It's too tightly bound. You just make more mesons if you try to pull it apart. So SU3 color with 3 colors and everything being a color singlet. Then a development that I haven't talked a lot about yet, but we need to look at in some detail because it puts some serious constraints on the standard model. SU2 cross U1. Now, those are not the weak symmetry and the electromagnetic symmetry. Originally, yeah, they were. We've looked at U1 gauge theory. We mentioned SU2 gauge theory, but SU2 cross U1 is the symmetry of the electroweak group. And among the generators of SU2 and U1, you have 2 diagonal generators, right? The sigma 3 of SU2 and the U1 is diagonal. That commutes with everything. The photon and the Z0 particle are linear combinations of those 2 diagonal generators. So the photon is not the U1 gauge particle. The photon is a linear combination of I3 from the SU2 and the U1 generator. Similarly, the Z0 is the orthogonal linear combination. So one of the things we'll need to talk through is, well, okay, so what are the particle states of the electroweak mode? But this is a good starting point, right? We're going to do a gauge theory of those symmetries. And how do we do it? All right, let's use all the fancy things we know now about gauge theory and take a group quotient. So I want to take the Poincare group, and I want to take SU3 and SU2 and U1. And that includes all the symmetries we want. Then I'm going to take a quotient by the Lorentz group. Poincare over Lorentz is going to give me a Lorentz invariant gauge theory, right? If we don't add curvature, we're just talking about Minkowski space from the quotient of those 2. I think we looked at that briefly. Did we look at that? We looked at that. Do you remember whether we looked at that or not? We can talk about it. Okay. So cross, right? Remember, what we take a quotient by here goes on the fiber. So remember fiber bundles? All right. So if I take that quotient is basically a 4-dimensional manifold. And that's basically described by the quotient of Poincare over Lorentz. Poincare includes translations and Lorentz transformations, and Lorentz quotients out the Lorentz and leaves a 4-dimensional manifold, which is spacetime, right? So if we just look at Poincare and Lorentz, the Maurer-Cartan equations for those look like this. And it's not too hard, if you know the Frobenius theorem and understand the Maurer-Cartan equations, to show that this describes space-time, right? When we do the quotient group, we're talking about the subspace spanned by not the Lorentz generators, the other 4, right? Well, to solve this equation, you can first notice that this is an involution. D of omega lies among the omegas, which means that omega equals 0 is a solution, but more generally from the, well, just solving that equation on its own, it's D of some 6, think of these as anti-symmetric with lambda inverse CB. This form gives a general solution to that equation. The involution, the fact that this is involute tells us that there are 6 coordinates, one for each generator, and that these omegas can be written as proportional to the differentials of those 6 coordinates. Well, those coordinates are Lorentz transformations. And if we hold lambda constant, then this goes to 0, and the equation we're left with is dE equals 0. That tells us immediately by converse to the Poincare lemma that E is exact and can be written as differentials of 4 coordinates x. Well, the E's are an orthonormal basis. We choose them that way to be orthonormal. There's, they're always some linear combination of differentials of the coordinates. They're one forms, but they're orthonormal. But this says that our orthonormal basis is also a coordinate basis. The only time you have a coordinate basis that is also orthonormal is in flat space. So this tells us, this equality tells us that, in fact, we're talking about a flat space. All we have to choose is the manifold, and let's choose the manifold to be R4, and then we're in Minkowski space. With this norm. This norm is preserved by that Lorentz connection. We know that a priori, so we're allowed to choose it. Let's say there are theories where there's actually a prediction of what that ought to be, but we're not there. So this quotient is still going to have that, but then that means this M4, R4 with Minkowski metric, right? That's flat space-time. But we have a fiber bundle here with the quotient of everything still on the fiber. And what we have created here is an arena where we can choose SU3 across SU2 across U1 gauges arbitrarily. We can choose them different at every point. So we've created the arena in which every gauge theory of these guys lies. And so that's the mathematical arena for all of this. Now we want to modify these equations to get fields, and that's going to be the next step. But the real physics enters when we write an action out of those fields. So the next thing we do, we want the Maurer-Cartan equations for the whole thing. So I've discussed the Poincare and Lorentz, where these are the forms dual to Lorentz generators and translation generators. These are one forms dual to those generators of the Poincare group, for the algebra of the Poincare group. For the other symmetries, well, for SU2, we can choose generators to be the Pauli matrices, and we know that I want to keep my indices consistent. Since we have 4 different groups going here, we might need a different set of indices for each different set of generators. So let's choose I for the SU2 symmetries. By now, you've gotten used to living in 3 or 4 different spaces at once. So we're definitely doing that here. This is a lot of symmetry on these fibers. And so we could have objects with an index from each of these things. We could have a Lorentz vector, which is also an SU3 something, and an SU2 something, and a U1 scalar. So, we could have lots of different things happening with any one field. So it won't be that complicated, but it could be. All right. Then we have, for the SU3, we have the 3. We have the Galvan matrices, which now become A and B, where we're going to pretend that A and B and C and D are from a different alphabet than I and J and K and L. Right? So we know which space we're in. And these satisfy a similar thing to I, where now we have the F, CAB, and the C, something like this, where these are the structure constants of the of SU3 with the Galvan matrices. All right, we've done Poincare, and the U1 only has one generator. So now we choose one form's dual to all these generators. So, I should have said for Poincare, okay, we've got Lorentz generators and we've got some translation generators, P. And so there are, for the Lorentz generators, we have some dual one forms called the spin connection. And these are going to be 1 if A equals C and B equals D, or -1 if A equals D and C equals B, something like that. A -1/2 here might be good. Then dual to the translation generators, we have the solder form. And now dual to the SU2 generators, we're going to introduce, what did I call them? Some one forms BJ, delta JI. Then dual to the Galvan matrices, we're going to introduce, what did I name them? G. What does G stand for? Gluon. We're getting close to physics here, guys. These are gauge fields. These are particles we're writing down now, right? So those are the gluons. And then for the single generator, let's call it Y. And yes, it's hypercharge. We're introducing hypercharge in a different way than we did back with the flavor models, right? It's still hypercharge, but hypercharge is now the sole generator of the U1 in the standard model. And dual to it, we have some one form B, gives us 1. So this defines the connection fields for our unified model. And so now we write them our Proton equations, and they're really important. So you totally remember the Maurer Proton equations, D of any of our basis forms, we have -1/2 times some structure constants with omega B, which omega C. That's always the Maurer Proton equation. Whatever group you're dealing with tells you what these structure constants are. You make them real or keep track of where you let them be something different. But what we're going to do is we find the Lie algebra of all of these. Well, we've got the Lie algebra of all the groups. And we use those structure constants in this equation to write the Maurer-Cartan equations. So here we have Maurer-Cartan for gravity. And then for the other interactions, let's see, we have the gauge fields of SU3, which become gluons. And so -1/2 times structure constants, GB, GC. And there are no terms here that are like a G with an omega or a G with an E or a G with a any of the B's, because these are direct product groups. All the generators from SU2 commute with all the generators from SU3. You know, there are no cross terms in any of these. In a unified field theory, there would be cross terms where some of the SU3s coupled to the SU2s and so on. So having this language enables us to look at alternative models, right? Having a nice way to formulate this model lets us think about other models very plainly. And then finally, there are no structure constants for the U1, so we have D of B is 0. So those are the Maurer-Cartan equations for our standard model. Now we want the Cartan equations. So the general procedure is to change the connection forms. Well, you know, these guys are all the connection forms. You know, the G's, the B's, you know, all of those are Lie algebra valued 1 forms. Now we're going to change them, right? If we want to do the standard model in curved spacetime, we're going to get curvature here, maybe torsion there, and you want to work with the standard model in an Einstein-Cartan space where you got torsion. No, you don't, but you could. You know, you would add the torsion here. The Riemann curvature goes here, and we're not going to do quantum field theory standard model in curved spacetime. We're going to keep it flat because, like, whoa. But when we modify these connections, right, these now become the Cartan equations. And what happens is, right, if I change G, it no longer satisfies this. There's going to be some field here. And I'm going to call it, what did I call it? I want to keep my notation consistent here. Oh, big G. And here, let's call these F sub I. And this is no longer 0. It's going to be something which I call H. These are now the Cartan equations, the flat space Cartan equations. But now we've introduced field strengths for the gluons, the W and Z particles, and the photon. They're all in there. In a Feynman diagram, you know, where you've got some particle emitting something, well, you know, this could be like some combination of these B's. Or if we have a strong interaction, we're going to depict these G's by a curlicue line. So we draw a line like that for the gluons, right? So we're making contact here with, you know, the kind of field theory that we did at the end of last semester. Now we can write these out. Are you guys keeping up with the reading and the exercises and all that? Don't be shy. It's summer. I know.
Yeah. I didn't do much this last week here, but
yeah, I get
back up for sure.
Yeah, I spent most of this week running a track home, building a trail across the front of our property here. But you know, it's summer. I mean, you know, you got to enjoy the summer, right? And probably you're doing some research and who knows what all, but, you know, you want to learn this, you know, at least do the reading, and, you know, the exercises aren't hard. So it'll get your hand in it. Let's see what these fields look like. All right, now I think we've, let's see, we talked about Yang-Mills fields. Did we talk about Yang-Mills fields? I'm not sure we've done much with it. So let me do one of these, and I'll leave another for an exercise for you. But if you want to take these equations and make them look like the Faraday tensor, say, right? Well, what happens? That's here. So let's take this G, and what is it? It's a two form. So it's going to be G dGA plus a half, and these F's are the structure constants of SU3, which, you know, is some totally anti-symmetric thing, which we can work out by taking commutators of the Galvan matrices. Then with GB and GC. So we want to turn this into something, well, we're in flat space-time. And to make this look more familiar, let me choose a coordinate basis. So I could expand in terms of the orthonormal basis, the E's, but let's expand in terms of just the coordinate differentials, dx mu wedge dx nu. And now this is the field strength. This corresponds to the Faraday tensor for E and M, but there's one for each generator of SU3. So there are 8 of these fields. These are the gluon fields. On this side, dg is d mu g a nu, but we want to anti-symmetrize. So I'm going to explicitly anti-symmetrize d nu g mu a dx mu wedge dx nu. And then this, we have a half f abc, then g mu b g nu c dx mu wedge dx nu. This is fun. I should lecture from the rolling chair on it. Okay, so now that everything is explicitly anti-symmetric in mu and nu, I don't need to keep the basis forms anymore. It's just an anti-symmetric tensor. I can cancel a half, and I have, for each generator, Ga mu nu is d nu G a nu minus d nu G mu a plus f abc G mu b G mu c. And that's what a non-abelian gauge field looks like, field strength looks like. All right, if you were dealing with U1, it's abelian, there are no structure constants, and that just reduces to the Faraday tensor. There's only one generator, then that would be F mu nu, the electric and magnetic fields. But here we have that kind of structure with 2 important differences. One, there's one of these fields for each generator of the group, each dimension of the group. And for a non-abelian group, you have this term that's quadratic in the potentials. Now, this object is a tensor under SU3 transformations. And that's the kind of thing that we can put in an action. So I asked you as an exercise to write out F and H this way. Well, you can write it down immediately. That's just getting you to write what I've just written. So do it. That's easy. Now, what have we got? We have a principal fiber bundle over flat Minkowski spacetime over Minkowski spacetime with local Lorentz, where for Lorentz, we want to take spin 1, 3. We want the spinner representation of the Lorentz group because we want to use spinners. But we've constructed direct spinners. And we know how Lorentz transformations act on those. So that's fine. Then also as a fiber symmetry, we have SU3 and SU2 and U1. So we have this structure where we can do local Lorentz, SU3, SU2, U1 transformations, different transformations at each point. And because of that, we were able to introduce these curvature fields or field strengths that describe the physical properties. Those are gauge invariant field strengths. And so we can include those in our physics. So now we want to write an action. And there's a fairly obvious choice. It's not quite right, but we'll start there. The first thing you want to do is to assess what are the tensors, what are the objects from which you can build an action. You always want to use covariant objects to build your action, unless you do some fancy topological stuff, which there is a little bit that's really very cool and interesting, but takes us afield. But the tensors, the things that transform linearly and homogeneously under these various groups, are the things that we want to include in the action. So what are they? Well, they are the various fields, right? We can have G and F and B. We could use their duals, their Hodge duals. We have the Minkowski metric. The solder form is a tensor because we don't have translational, well, we do have translational symmetry, but anyway, we can use it. What other objects can we build our action from? Well, do you remember what a representation is? Any vector space that the group acts on is a representation. We can use any representation of any of these groups. So what's the vector space that the Lorentz group acts on? Well, Dirac spinors. So we can include Dirac spinors. They could be SU2 valued if we like. SU2 acts on doublets. So we could have doublets of spin fields, and those would be acted on by SU2 and by the Lorentz group. That, in fact, is what we do for the quarks. We introduce up-down doublets. In fact, all of the quarks, you've seen the pictures, right? You know, all the quarks and leptons occur in pairs. Those pairs are acted on by SU2. Then let's see, what other representations? Well, scalars, right? So U1 can change any field by some power, an exponential e to the I times the hypercharge, right? So it's a phase effect. So if G, let's not use G, let me find H. So suppose H is an element of the U1, right? We can write that as e to the I times the hypercharge. If we make hypercharge Hermitian, which I guess makes it real, right? But then if I have some field, it may have a weight. It may have a certain value of the hypercharge, hypercharge 3. All right, so suppose this has hypercharge 3, then it's going to transform as either the 3i size. So it picks up a phase factor with an appropriate weight to how strong its charge is. So this is the cast of characters. These are the objects that we're going to build a theory out of that will be the standard model. So what do we write for an action? We've already talked about the action for a Yang-Mills field. All right. Bye-bye. Proton and proton. So, right, we have these various field strengths. We can take as an action GA wedge GB, right? These are two forms, so in 4 dimensions, right, that would be a total divergence. But if I take the Hodge dual, that's basically just G mu nu with GB mu nu. So the spatial indices contracted. It has to be a scalar in SU3 as well. But for the unitary groups, there is a metric on the Lie algebras. And because you can do unitary transformations, you can diagonalize that metric and rescale it to be the identity. So basically, we can just take the identity here. Let me call it delta AB. We can take that as a metric on these guys, or we can just think of it as a Euclidean inner product, and you can put them on the same level like that. Or you can write one up and one down if you want to keep track of the fact that we really are using a metric here. Okay, so we could have that. We could do a similar thing for the Fs and the, let's see, and B. So each of those is some 4 form. So these are scalars, right? Now, how do I know these are scalars? Because they're scalars under their respective groups, because I've used a group invariant object to contract the group indices, just like we do in general relativity, right? You use the space-time metric to contract indices, and that forms a Lorentz or general coordinate invariant thing. Well, we're doing the same thing here. We have metrics on those internal spaces, so we can use it to contract these indices. And then the fact that we have a 4 form means we're writing a scalar. 4 forms are dual to scalars under the Hodge dual. So since it's under an integral sign, really it should be a 4 form. But these are dual to Lorentz scalars. And that's why when you work out what G star G is, you find that the Lorentz indices are contracted, fully contracted. So those are all Lorentz scalars. So this is a legitimate starting place for an action. And ultimately what we're writing is something like this, where we've contracted those and Fi mu Fi mu and gamma B mu nu B mu. So in coordinates, if we expand things out, this is what we're writing, which it might be what you would choose to write down in the first place anyway. What else can we have? Well, we have, most importantly, we have spinors. So we can write some Dirac fields, right? So we know how to write Dirac fields. psi bar I d slash minus m psi. Okay, but what if we have multiplets of these guys? Well, then we need a covariant derivative here, d slash, and then these can have these might have SU3 indices or SU2 or U1 indices on them. So this derivative needs to be covariant with respect to whatever space this goes in. So if we want in the action a term like our up and down quark with some sensible sort of operator and an up bar down bar quark here, we want a term like that where U's and D's interact with one another. Then that comes from the gauge connection here. So a covariant derivative with respect to SU2 is going to put a connection, what is it? It's the potential for this F, so it's going to be BI. BI, any of those guys, but with the generators, sigma I. So that's the kind of matrix that goes in here. And then it's a one form. There's a space-time index on this. Well, this is a slice, so there's a gamma mu. So this covariant derivative, if we have, say, SU2 doublets in our spinor action, then the interaction term that makes this locally invariant is going to be, okay, we have a doublet here, conjugate. We have gamma mu v mu Lie algebra valued one form with right. This is summed over the generator. I need a different kind of index here. Sorry. B. This is sum I, and then we need AB here, where that index is, one of these indices is actually down because I've used the spinor metric here to lower the spinor index. So the capital A is a spinor index, summing over the four components of a Dirac spinor. Then B is a collection of, it's a Lie algebra valued one form. One form I contract with the gamma, but then this is going to use SU2 to mix the components of this doublet with the components of that doublet. So oh wait, I've got too many indices at once. Hang on here. Let's see. Let's suppress the spinor index that runs 1, 2, 3, 4, and think of this as A and B running 1 to 2. So we have 3 2x2 matrices that are mixing up and down here with up bar, anti-up and anti-down there. So we have a pair of spinors here, right? B runs 1 to 2. That's telling us whether it's the up or the down. Those get mixed by the gauge fields and can spit out up or down over here. So, right, what is this gauge field? That's a W or a Z particle or part of a photon, right? Let's suppose it's a W particle. So what I have is an up quark coming along, emitting a W particle, and being a down quark going out. So let's see, this is plus 2/3 minus 1/3. So we've lost 1 unit of charge. And there's a Feynman diagram from that, which comes from the SU2 covariant derivative here, which is one of the allowed things we're allowed to put into our theory. So this is the starting point. We can add we can add whatever fermions we like. Well, we pretty much know what fermions we would like. We know they come in doublets. And let's write that list. Up and down, charm and strange, top and bottom, then the leptons with their neutrinos, the electron, the mu1 and the mu neutrino, and the tau and the tau neutrino. And we've introduced interaction fields. We have the BI mu and the B mu and the G A mu. There are 8 of these gluons, and there are 4 electroweak gauge bosons called there's called intermediate vector bosons. Big long name that no one uses. So these are the basic elements. And we're going to have to fuss with this a bit. Now we're running long here. You guys bored yet? But let me say just a little bit more where this is going to go. So we can write an action. We can stick in appropriate coupling constants. One would think that in the Dirac equation over there, where am I pointing there? You stick in the mass of the particles you're interested in, and everybody's happy. And what is it? Is Bob's your uncle? Is that what they say? Bob's your uncle. The British always say that. Okay, yeah, you don't watch enough British mysteries. It comes from, it's a political thing. Some politician got a job because Bob really was his uncle. Robert of so-and-so and such was his uncle, and it was a clear case of nepotism. So, if things go smoothly, Bob's your uncle. All right, but anyway, we run into a problem. The gauge fields. In order to have, in order for these G star G, F star F, in order for those to all be gauge invariant, it's not straightforward for the particles to have mass. So none of these gauge bosons here can have mass. A mass term in the action, we've seen it, right? You put in the mass and you put in the square of the field, something like this. And that would give a mass to the B particle, but that's not gauge invariant. You can't stick that in the action, right? Because this changes by, it's a connection. It changes by a gradient, DGG inverse thing here. Right, so there's more. This B squared changes if you change your local SU2 gauge or your local SU3 gauge. Well, that's fine for the strong interaction because, as far as we know, gluons are massless. If they had a little mass, it wouldn't make a whole lot of difference anyway because the energies are so much higher than the masses. But as far as we know, gluons are massless. No problem. How about the electroweak particles? Well, the photon's massless, but the W and Z have masses of 80 and 90 GeV. They're much, much heavier than the baryons. They're really massive particles, but you can't add a mass term for them. There's another problem. The weak interactions violate parity. And that means that you, instead of writing just psi bar d slash psi, instead of a gamma mu in the slash there, you have to use a parity projection, which involves it's a 1 plus or minus gamma 5. We talked about those parity projections back when we looked at the at spinners in the drag field. And you have a feeling we've covered a whole lot of new stuff that you haven't encountered before. This is, this training should start earlier, I think. There's too much new material. But you guys are on top of it. You're sharp, you're dedicated, you're fascinated, and you can easily go back and remember about those projections for parity. 1/2, 1 plus or minus gamma 5 projects left and right-handed spinners. And so that has to be folded in to that spinner action. Well, that's a problem because, suppose I stick in a 1 plus gamma 5 here, or probably 1 minus gamma 5. Okay, so that, actually that one would be a plus. There's a gamma mu in here in this d slash. So if this particle has a 1 minus gamma 5 on it, sign, to make that a left-handed spinner, let's say. We want something that violates parity, so we want to write the interaction. Right? The interaction is sitting in the connection here. And that interaction should involve left and right-handed spinners differently. Then when we take the conjugate over here, I5 is going to change to minus I5, and so we have 1 plus gamma 5. And that's fine because if I pass that 1 minus gamma 5 through this gamma mu, it changes to a 1 plus gamma 5 because gamma mu and gamma 5 anti-commute. And then I get a projection squared, which is fine, and everything's kosher. But what about the mass term? There is no gamma sitting here. So that projection and that projection are orthogonal and give 0, which means the mass term drops out of this equation if we work only with left-handed or only with right-handed spinners. So we can incorporate the parity violation by dealing differently with left and right-handed spinners, but now they can't have any mass either. So everything in our theory's got to be massless, except that we know perfectly well they're not. So we need to introduce another mechanism, something that will give us mass, and that's where the Higgs comes in. And you may have heard that story, and we're way past our usual 2.5 hours now, so I won't tell that story today, but we'll talk about the Higgs in detail as we get there. But that's a major modification, and we need for that, if that Higgs is going to come in such a way as to provide masses, then not only do we need to do this, to couple it to the weak gauge bosons, we also need to give the quarks and leptons masses. Because by using only left-handed spinners here, we have to drop the mass out of the Dirac equation. We can't just stick a mass term in there either. And so we need some kind of coupling between the Higgs and all of our fermions. And that's provided by what's called a Yukawa interaction. And we'll talk about the Yukawa interaction. But we'll do that a week from Monday, because I got a trip to plan, and You guys have been listening patiently for 2.5 hours, and all of that. Read the book. I will post new stuff. I know it's summer, but this is cool stuff. So, I think chapter 13 does a good job on the on all the flavor stuff. And let's see, I'm right now I'm editing the chapter on the standard model. So as soon as I get that done, I'll post that and I'll send around an email to that effect so that you can read that as we talk about it. The next, I think the next two lectures are going to be on an iPad and my laptop. But that works. We should be fine with that. And then I'll be back in town and back. Hopefully by then I'll get my new computer working. So I can get this. I was looking at the image of me, and there are two big white screens behind me, but the other one's just a wall. So I forgot it was that. I'm not used to being off at this angle. Okay, so any questions? Anything I can tune up now? Okay, so stick with this. Do enjoy your summer, enjoy your holiday weekend, and eat a hamburger, whatever. But also, keep going with the field theory, and we'll look at some details of the standard model. And I think we can probably get through that, and then have time to talk a little bit about string theory. At least write an action, find the field equations for string, quantized a little bit. We'll see what we have time for with that, but I'd like to be able to talk about string theory a little bit at the end. So have a good rest of your day. Thanks for taking the time to come do this. We'll see you again a week from Monday, the usual time.